Good morning. My name is Mark Saltis. I'm here with my colleague James Stinninger, and we are from Earthrise Space Foundation. We're here to give you a preview of a system that we developed that is a method for optics-based guidance navigation for precision landing here. And our application is based for the moon. It can be adapted for multiple landing on terrestrial bodies. So let's first start with who we are. And we are the Earthrise Space Foundation. We are a nonprofit research lab located over here in the Central Florida area by the University of Central Florida. And the main motivation for the development of this technology is we are competing in the Google Lunar X Prize as Team Omega Envoy. And we have adapted this system to provide a low-cost solution to the lunar landing problem. And over here at Earthrise Space Foundation, we provide a unique opportunity to allow direct interaction with the university, to allow students like myself when I was an undergrad to come in and do internship work and get their hands on actual spaceflight hardware and see spacecraft design firsthand, especially as an undergrad. That's a very rare opportunity. And so what we're trying to achieve with our pinpoint lunar landing, and we see down here below is a landing ellipse. And so our goal is to deliver payload to the lunar surface at an altitude rate of less than 2 meters per second at touchdown. And with the ellipse you see below there, we're looking to shorten that down to about 100 meters. And in the case of Apollo 11, their landing ellipse is on the order of 20 kilometers, as you see here. And so how is this done before? Well, this isn't new by any means. We've put multiple spacecraft down to the lunar surface, dating all the way back to Ranger and Surveyor, where most of these types of systems were done inertially. And Apollo, which wasn't technically inertial because they did have an astronaut in there actually providing the hazard detection and avoidance. And so we'll come here, and that was to mitigate the need to fly with a LiDAR, just because of the tall order in terms of how long it takes to manufacture and also the system cost. And so we try to combat that, taking a little bit of what we see what Draper was doing and adapt that to our own. And so we were using an optics-based platform to do just that. And so what we can provide is a fully autonomous GNC suite that also provides train relative navigation and that uses a set of cameras, 2 CCD, narrow angle and wide angle cameras, and then couple that with our inertial suite, which would be a set of solid-state IMUs, laser altimeter, and a star tracker. And so we broke this down into 2 phases. It should be train relative navigation and hazard detection and avoidance. And James will actually walk you through the particulars of those and the 2 phases of TRN and the single phase of HDA now.
Okay, so our first opportunity to run the terrain relative navigation suite is once we've achieved the parking orbit of 110 kilometers. This allows us to verify whether orbital determination has placed the spacecraft in a nominal trajectory, and if not, allows us time for course corrections with minimal fuel consumption. Once the proper trajectory is achieved, the vehicle can begin powered descent. The second opportunity to conduct TRN is an altitude of 25 kilometers when the laser altimeter first makes contact with the lunar surface. Now at this point, the TRN suite provides position, attitude, estimate updates to the guidance algorithm. At an altitude of 2 kilometers, the spacecraft performs a pitch-up maneuver, and the autonomous hazard detection and avoidance suite takes over to verify whether or not the primary landing site is free of hazards. Here we have the braking phase of descent from an altitude of 25 kilometers down to 100 meters, at which point the system is running purely off of inertial measurements until touchdown. The green and yellow trajectories indicate which sensory suites are active during different phases of braking. Alright, so relative navigation is the process by which information obtained from the surface terrain relative to the spacecraft is processed and used for navigation. The goal of TRN is to provide full state estimation updates and trajectory verification for the vehicle. The first phase of TRN is conducted from a parking orbit, where images from the narrow angle camera are processed using crater detection and mapping and crater matching algorithms. The crater detection and mapping algorithm first identifies edges of potential craters, groups together edges associated with the same crater, fits an ellipse to that crater, and finally provides a confidence evaluation that the feature mapped is actually a crater. The crater matching algorithm then uses this information to correlate the craters being mapped with an onboard database to determine the spacecraft's current trajectory. This database is generated by processing imagery from the Lunar Reconnaissance Orbiter using the CDM algorithm prior to launch. The second phase of TRN begins at an altitude of 25 kilometers once the laser altimeter first makes contact with the lunar surface and can establish a moon-centered inertial frame of reference. At this time, images captured by the narrow-angle camera are processed using the CDM and optical flow algorithms. The OF algorithm works by tracking identified craters through successive images and calculating the position and displacement rates of each. The information generated by these algorithms is combined with the data from the altimeter and the IMU, then passed through an unscented Kalman filter in order to update the state of the spacecraft. The UKF is a probabilistic function that fuses information from every available sensor into a best estimate of the vehicle's current state with respect to the lunar surface. The goal of autonomous hazard detection and avoidance is to detect and avoid hazards classified as mission fatal during the final vertical phase of descent. Hazards include discontinuities, craters, rocks, or areas with excessive slope. During AHDA, images captured by the wide-angle camera are processed using the CDM and OF algorithms, with additional hazard maps generated using texture mapping and shadow detection algorithms. The texture mapping algorithm creates a roughness map by analyzing the albedo of the lunar surface. The shadow detection algorithm uses information about the sun elevation angle to identify shadows cast by rocks in order to determine their respective diameter and location. All data generated from the sensors is passed through the UKF and combined with the hazard maps to provide navigation updates to the guidance algorithm. In the case that the primary landing site is found to contain an unacceptable density of significant hazards, the nearest hazard-free site is selected for retargeting by the guidance algorithm. Once the spacecraft crosses the 100-meter threshold, the HDA algorithms no longer influence the guidance algorithm's decision tree. In order to test the hardware and software necessary for an optical-based approach, a two-part testing plan was developed. The first phase involved simulating descent and landing scenarios using NASA's program to optimize simulated trajectories to or post to for software integration. The second phase involves using a custom-designed testbed for hardware and software integration and testing. This setup features a pin joint and adjustable design to allow simulation of multiple trajectories. The platform that the sensors are mounted to slides down an aluminum track overlooking panels of simulated lunar surface terrain. The entire system is controlled by a mechanical winch. This CAD assembly depicts the preliminary setup for the proposed testbed. The sensor platform slides down the track towards the joint where it rotates in order to simulate the pitch-up maneuver and approaches the final panel in a fashion that mimics vertical descent to touchdown. The panels themselves are made out of foam and covered with lunar simulant in order to exhibit properties similar to the lunar surface. This testing setup will yield empirical results that will help validate our optics-based approach to a pinpoint lunar landing.
That kind of sums up the majority of the work that's been done here. That further work has been done that is currently, I guess, we're going to keep confidential at this point until a lot of the test data comes back and we can really start to discuss the robustness of the program as it is. One of the major contributions to this system is actually going to come in the form of the Lunar Catalyst provided by NASA, in which we have been able to achieve a nice set of resources here that have been made available to us, and a lot of that is going to come in handy to start really getting the system in place and preparing it for testing on the terrestrial test platform that is also under development now.